Good evening. Spring is the best time of year to observe the universe with amateur-sized telescopes. The constellations on view are rewarding since we are looking outside our own Milky Way galaxy to see clusters of galaxies beyond. While the planets are receiving a lot of attention at the moment, the clusters of galaxies now on view are worthy of equal attention. When dealing with galaxies, we have to come to terms with immense distances. Our solar system is made up of 8 planets, along with the dwarf planet Pluto, that are in orbit around the Sun, our nearest star. Our Earth is 150 million kilometers distant from the Sun, while Pluto orbits at 5 billion kilometers. Light travels at a constant speed of 300,000 kilometers a second, so the Earth is 8 light minutes from the Sun. Astronomers use the speed of light as a unit of measurement. In 1 year, a pulse of light travels about 9 trillion kilometers, and we call this the light year. On this cosmic scale, the nearest star to the Sun, Proxima, in the southern constellation of Centaurus, lies 3¼ light years away. The Hubble Space Telescope is celebrating its 25th anniversary. Hubble was launched on the 24th of April 1990 into a low orbit of 550 kilometers above the Earth, and it takes 92 minutes to travel around our planet. Hubble transmits about 120 gigabytes of science data every week and is sent back hundreds of thousands of images of the universe during its quarter-of-a-century lifespan for scientists to study. 2 of these images, known as the Deep Field North and South, have proved to be very rewarding for astronomers. Using these images, they were able to narrow down the age of the universe to a more precise value. Hubble has revealed the age of the universe to be about 13.7 billion years, which played a key role in the discovery of dark energy, a mysterious force that causes the expansion of the universe to accelerate. Hubble Space Telescope observations of very distant supernovae showed that, a long time ago, the universe was actually expanding more slowly than it is today. So the expansion of the universe has not been slowing due to gravity, as everyone thought. It has been accelerating. No one expected this. Theorists still don't know what the correct explanation is, but they have given the solution a name. It is called dark energy. To measure the distances of faraway galaxies, one method is to use exploding stars called supernovae as standard candles. Astronomers use a certain type of exploding star called a Type 1a supernova. Supernovae, which occur within a galaxy about every 100 years or so, are among the brightest events in the sky. When a star explodes, it releases so much energy that it can briefly outshine all the stars in its galaxy. There is one bright classical supernova on view at the moment. On March the 14th, 2015, amateur astronomer John Search of Chatsworth Island, New South Wales, Australia, discovered Nova Sagittarii on 3 images taken with a DSLR camera and 50mm lens. It was then of magnitude +6 and soon became a naked eye object. Its brightness peaked on the 21st of March and it is presently at magnitude +5.3. To find the distance to the galaxy that contains a 1A type supernova, scientists just have to compare how bright the nova explosion should be with how bright the explosion appears. Using the inverse square law, they can compute the distance to the supernova and thus to the supernova's home galaxy. Now a University of Arizona-led team of astronomers have found that these type 1a supernovae fall into distinct populations not recognized before. The findings have implications for our understanding of how fast the universe has been expanding since the Big Bang. Most importantly, the findings hint at the possibility that the acceleration of the expansion of the universe might not be quite as fast as textbooks say. We know how much dark energy there is because we know how it affects the universe's expansion. Up until this discovery was made, we knew that about 68% of the universe is dark energy. Dark matter makes up 27%. The rest, everything on Earth, all normal matter, adds up to less than 5% of the universe. It is therefore quite possible that there is a little less dark energy and more dark matter in the universe than previously thought. Fortunately, help is close at hand. In 2013, astronomers in Chile began mapping the distribution of dark energy in the universe and have just released their first results. They measured the barely perceptible distortions in the shapes of about 2 million galaxies to construct the new maps. The dark matter map makes use of the early dark energy survey observations and covers only about 3% of the area of sky that the telescope will document over its 5-year mission. The survey has just completed its second year. As scientists expand their research, they will be able to better test current cosmological theories by comparing the amounts of dark and visible matter. The Dark Energy Survey is designed to probe the origin of the accelerating universe and help uncover the nature of dark energy by measuring the 14 billion year history of cosmic expansion with high precision. More than 120 scientists from 23 institutions in the United States, Spain, the United Kingdom, Brazil, Germany are working on the project. This collaboration has built and deployed an extremely sensitive 570 megapixel digital camera known as DCAM. This new camera has been mounted on the Blanco 4-meter telescope at Cerro Tololo Inter-American Observatory in Chile.
I'm a member of the Dark Energy Survey Collaboration, and I'm here on Cerro Tololo working to help commission the new dark energy camera that we've just installed on the Blanco telescope. The whole purpose of our project is to understand what is dark energy. Dark energy was discovered just less than 15 years ago, actually. In fact, using, in part, this very telescope. And it was discovered by its effect on the universe. So dark energy is our name, and it's just a name that we give to the phenomenon that's causing the universe's expansion to accelerate.
We're not trying to figure out if dark energy exists. We're not trying to find it. We know dark energy exists. We're trying to characterize it. We're trying to understand what it does to us, what it does to the universe, to its expansion rate, and to the gravitational attraction of things like galaxies.
I work with the Dark Energy Survey, and I am working on CISPI, which is the software end of the camera. And right now we are in the control room for the camera. As you can see, here are our lovely displays. We're doing a survey, so we want to cover a large section of the sky.
Over 5 years, the Dark Energy Survey will scan 5,000 square degrees of sky, far back in time and far away from us, in order to measure the distances of supernovae and the distributions of galaxies.
Since we're covering a large section of the sky, we've got to move the camera to cover all of it, and we have to track the sky as it moves because the sky moves very fast, and we're doing long enough exposures that if we weren't following the sky as it moved, it would get blurry. We are at an observatory, and we're looking at the stars, and you don't see the stars in the daylight. So generally, the observers will start working sort of around twilight, around dinner. You can start taking some calibration frames and dome flats. You can do those when the daylight's out. But you can't open the dome till after dark. And so right now, it's about 12:20, and this is very early in the night for an astronomer. And so an astronomer will generally stay here and work until sunrise when you can't take any more data.
Every time I come to Cerro Tololo, I realize how special an experience it is. Last night when we were looking up at the sky, and when you could see the Milky Way so clearly, but you know that as a galaxy it's a line. You know that the plane of it is a line, and you see it curved across the sky. What else can that do to you but make you feel like you're on this sphere with all these other people, with the people here on the mountain, but everyone else. Like, you know that you're home in so many ways.
This job is a whole lot of fun. I've really enjoyed seeing from, at first, all I was seeing was the software and it was very abstract, and it's been really neat to see first the telescope simulator being built at Fermilab, and then just to come here to Chile and be able to actually see the telescope take data. It's really exciting.
In some sense, the purpose of our experiment and what we'll learn by understanding more about what dark energy is to find out about the fate of the universe. What is going to happen into the future? Is the universe really going to keep expanding faster and faster and faster, or not?
Over 300 people, from professors to engineers to students and postdocs, putting together the Dark Energy Survey and all the infrastructure from simulations to theory and everything that went into making the survey possible. One might think, oh, and I'm just one little piece in this large process. But when you think again about what we're exploring, when you think about the images that we're going to take, when you think about how far and away and how far back in time we're going to look, you can't help but feel like you're a part of something that's really important, that's helping us see not just about the past of the universe, but the past of us, where we've been and really where we're going to go.
Hubble has shown scientists galaxies in all stages of evolution, including young galaxies that were around when the universe was still at an early stage, helping them understand how galaxies form. It found protoplanetary disks, clumps of gas, and dust around young stars which are alien solar systems in the process of formation. The Sun is only one of at least 100,000 million stars in our own galaxy, and it is totally ordinary. It appears foremost in our skies because it is so near to us on the astronomical scale. During spring evenings, the Milky Way is low in the sky, passing through Cassiopeia in the north and Gemini in the west. In midsummer, it will have ascended high overhead and become very prominent in the summer sky after sunset. Our galaxy is an immense system. If it could be seen edge-on, it would give the appearance of being shaped like a double convex lens, or less scientifically, but more graphically, like two fried eggs clapped together back to back. There is a definite nucleus, and the Sun, together with its planets, lies well out towards the edge. Until recently, the size of our galaxy has been given as 100,000 light years in diameter and a maximum thickness of about 20,000 light years, with the Sun lying at roughly 25,000 light years from the centre. The Milky Way galaxy is now known to be at least 50% larger than this, according to new findings that reveal that the galactic disk is contoured into several concentric ripples. The research conducted by an international team led by Rensselaer Polytechnic Institute Professor Heidi Jo Newberg revisits astronomical data from the Sloan Digital Sky Survey, which in 2002 established the presence of a bulging ring of stars beyond the known plane of the Milky Way. The findings show that the features previously identified as rings are actually part of the galactic disk, extending across the width of the Milky Way to 150,000 light years. As well as its multitude of stars, the galaxy contains other kinds of objects. In particular, there are the misty-looking patches, which are known as nebulae, from the Latin word meaning clouds. These nebulae were studied during the 17th and 18th centuries, and catalogues of them were drawn up, of which the most famous was due to the French astronomer Charles Messier. Messier's numbers are still used. Thus the nebula in Orion's sword is M42, while the nebula in Cain's Venetici, the hunting dogs, is M51. At a fairly early stage, it was realised that the nebulous objects were of two distinct kinds. Some, such as M42, look like masses of glowing gas. Others, notably M51, seem to be made up mainly of stars. Sir William Herschel, the greatest observer of the late 18th century, made the inspired guess that the starry nebulae might in fact be separate galaxies lying far beyond our own. Proof was not forthcoming for more than 100 years after Herschel's death, but his speculation has been shown to have been correct. Shortly after the First World War, the American astronomer Edwin Hubble undertook a close study of the Andromeda Nebula, M31, using the 100-inch reflector telescope at Mount Wilson Observatory, then the most powerful telescope in the world. This galaxy is now on view to amateur astronomers living in the southern hemisphere. Hubble was particularly interested in some special stars known as Cepheid variables. Ordinary stars shine steadily for year after year, century after century, but the Cepheids brighten and fade over short periods of a few days, behaving with clockwork regularity. It was known that the real luminosity of a Cepheid is linked with its period of variation, with the more luminous stars having the longer periods. Consequently, the distance of a Cepheid could be worked out simply by observing it. Finally, Hubble managed to detect Cepheids in M31, and at once it became clear that the Andromeda system was much more remote to be a member of our own galaxy. This was a discovery of vital importance, since it meant that the other starry nebulae, too, must be galaxies in their own right. Between the work of Herschel and Hubble, another discovery had been made. In 1845, the Irish amateur Lord Rosse had set up a large 180 centimetre, that's 72-inch, reflecting telescope at his private observatory at Bear Castle, and it was found that many of the starry nebulae were spiral in form, not unlike Catherine wheels. This applied to the Andromeda object, but here the system was clearly placed at an angle so that the spiral effect was partially lost. He carefully observed Messier 51 and named it the Whirlpool galaxy, and today it is within easy reach of amateur-sized telescopes. M51 lies near the tail of Ursa Major, the Great Bear, which is high overhead during spring evenings, and there are three other galaxies on view in Ursa Major: M101, the Pinwheel Galaxy, M81 and M82, also known as the Cigar Galaxy. Let me show you where to find them. Using Ursa Major as a signpost, the Pinwheel Galaxy M101 lies below the star Alciad in the tail of the Great Bear, and the Whirlpool Galaxy lies above it in the constellation of Cain's Venetici, the hunting dogs. M63, the Sunflower Galaxy, lies nearby. Now join the stars Gamma and Alpha in the bowl of a dipper with an imaginary line and follow this an equal distance, and you will come to M81 and M82, which are visible in a low power eyepiece. The so-called local group of galaxies is made up of the Clouds of Magellan, the Andromeda Spiral, M31, the fainter Triangulum Spiral, M33, and a couple of dozen much smaller systems, in addition to our own galaxy in which we live. Other groups lie at much greater distances, and photographs show that the galaxies in them are of various forms. Some are Catherine wheels, some are barred spirals in which the arms extend from what seems to be a rigid bar, some are elliptical or globular, and some are quite irregular in outline. Undoubtedly, the spirals are the most beautiful, particularly when seen face on, as with the famous Whirlpool galaxy in the little constellation of the Hunting Dogs. The spiral structure seen in many of the galaxies is immensely significant. It is not yet fully understood, but at least it seems to be the kind of aspect which would be expected, bearing in mind that the galaxies are in a state of rotation. This applies equally to our own galaxy. The Sun, together with the planets, takes some 225 million years to complete one journey around the galactic centre. However, there are various problems. It is thought that the development of spirals depends upon the presence of dust and gas, and does not occur when all the material in the system is collected into stars. So there must be forces which impart a kind of rigidity to some of the structure. It is by no means easy to explain all the different forms to be seen in the different galaxies. However, dark matter must play an important role. At the centre of most galaxies is a black hole, created from the explosion of a dying star. A black hole is so massive and its gravity so great that not even light can escape its grasp, while nearby stars and gas fall inside, feeding it. Astronomers are confident that our own Milky Way galaxy has a supermassive black hole at its centre, 26,000 light-years from the solar system, in the region called Sagittarius A. It is believed to have a mass of 10 million times greater than that of the Sun, which is confined in a region of space the size of the Earth's orbit, of 150 million kilometres. What is seen is not the black hole itself, except observations that are consistent only if there is a black hole present near Sagittarius A. In the case of such a black hole, the observed radio and infrared energy radiates from gas and dust heated to millions of degrees while falling into the black hole. Although other possibilities exist for how these gases emit energy, interaction with a massive source of gravity is the simplest explanation. On January 5, 2015, NASA reported observing an X-ray flare 400 times brighter than usual, a record breaker from Sagittarius A. The unusual event may have been caused by the breaking apart of a solid body falling into the black hole, or by the entanglement of magnetic field lines within the gas flowing into the black hole itself. In the universe, some of the spirals are tightly wound, while others are decidedly loose. So far as our galaxy is concerned, we are now confident that it takes the form of a rather loose spiral with the Sun lying near the edge of one of the spiral arms. Our main knowledge has been derived from the science of radio and infrared astronomy, since radio, along with infrared waves, unlike light waves, are not blocked by the obscuring material. Of course, by no means all the galaxies are spirals. There are many systems without a trace of spiral structure. In general, these elliptical and globular galaxies seem to contain relatively little interstellar dust and gas. The formation of fresh stars seem to be confined mainly to the spiral arms, so that the elliptical systems give every indication of being more advanced in their evolution. It is tempting to suggest a galaxy develops spiral arms at the early stage, losing them when most of its star-forming material has been used up. But this idea has been generally rejected. For one thing, the giant ellipticals appear to be some 30 times more massive than the spirals. Astronomers at the European Southern Observatory in Chile have now shown for the first time how star formation in dead galaxies sputtered out billions of years ago. The observatory's Very Large Telescope and the Hubble Space Telescope have revealed that 3 billion years after the Big Bang, these elliptical galaxies still made stars on their outskirts, but no longer in their interiors. The quenching of star formation seems to have started in the cores of the galaxies and then spread to the outer parts. So far as is known, the galaxies spread through the whole of the observable universe, and they can thus be used to explore space on a very large scale, out to distances of thousands of millions of light years. Some of them present special features. In particular, there are the so-called radio galaxies, which emit radio waves very strongly. There are galaxies which appear to be expanding, and there are also the mysterious quasars and blazars. A quasar does not look in the least like a galaxy, but if distance measures are to be trusted, it seems that a typical quasar shines with at least 200 times the luminosity of a typical large galaxy. Amateur astronomers working with modest telescopes tend to concentrate upon our neighbours in the solar system. This is natural enough. The moon and planets show definite surface details, whereas no telescope of amateur size will show any structure in a galaxy. All modern professional work with regard to the galaxies is carried out by photographic means. Yet it is always worth searching for these remote systems and identifying them, as the amateur can gain a great deal of personal satisfaction, while there are always supernovae waiting to be discovered. If you are interested in astrophotography, I recommend Astrophotography magazine, which is free to read online. Please visit the website at astrophotography.net. I am most grateful to all the astrophotographers who have contributed to this month's programme. Here again is a look at their images. The Whirlpool galaxy, like others of its kind, contains thousands of millions of stars, and it is impossible to doubt that many of these stars must be attended by inhabited planets. There must be astronomers too, living in the midst of Messier 51 and using telescopes, and they will be able to see our galaxy as a faint, blurred spiral of light in their sky. That is all we have time for this month. Please visit our website, Vimeo, where you can watch all the past shows of astronomy and space. And if you like this program, please share it with your friends and members of your local astronomical society. Until we come back next month, good evening.